did omit a couple of words, which fortunately I think I kept on my slide, which I'm just the CTO for global provider mobility, not the whole of the company. The whole of the company would dwarf me by a huge number if I tried to even tackle it. But thank you very much for actually inviting me to speak here today. I believe it was a presentation I gave in one of the NOGs that kind of triggered this. But what intrigued me was the title of the conference, More IP. We've been hearing about cloud AI. We're networkers. I'm a networker, and AMS-IX is very much a networker. So let's get back a little bit into networking, because there is a really, really big shift happening in the networking world, driven to a very large extent by our cloud brethren, but we as networkers are going to have to deal with pretty soon. Okay, so we're going to talk today a little bit. I'm told I actually have more time than I thought I would be, but I'm still going to try and finish in the 30 minutes and not keep you from beer, which I think I'm the last thing standing between. So we're going to talk a little bit about what in the last 5-6 years has been emerging as the new internet, which is predicated on a different protocol stack that is running more and more over our networks. And what we're trying to do in order to actually deal with this new reality, because there is a new reality in a number of different ways. So let's start with what's happening around the world. And the story begins around 2020 for us, to a large extent, when a large service provider came around and said, okay, here is about 6 months worth of call flow records. It was a mobile service provider. And something is happening in my network. Can you analyze it, please? And what we found was some things that we all knew. Encryption had gone through the roof. Everything is in some way encrypted. That's fine. 10 destinations were 70% of the traffic. Later measurements that we've done have shown that 12 destinations are actually over 80% of the traffic in the global internet, which implies that there's not much of an internet anymore. There's 12 parallel private internets running on one common infrastructure and competing for it, as we're going to see when we do the protocol analysis. DNS was the load balancer of the internet, but there was something strange called QUIC rearing its face. I mean, I started working in this space in 1985, shows my age, and it was called the ARPANET, not even the internet at the time. The name was changed later, and always it was TCP/IP. Okay, there was UDP as well, but it was TCP/IP. What's this QUIC? Hold on. Oh, it's an acronym invented by Google, but that the IETF declined to accept as an acronym and took as a name. It stands for Quick UDP Internet Connections. But the protocol is actually now QUIC, a word. It's not an acronym, because they don't like the self-repeating acronyms like GNU and whatever. So this was a first inclination that something was happening on the internet. So we started looking around and started developing a little bit more of a more efficient measurements capability, so that we don't have to analyze months and months of call detail records to generate this kind of information. Jump 18 months later in a Nordic carrier, and what are we seeing? We're seeing that QUIC has almost doubled in its volume around the world, and for some players, it's already become the default thing. It was invented by YouTube. Actually, the team that first proposed the QUIC protocol was YouTube, so you kind of expect YouTube to default mostly to QUIC. What was really surprising was that Meta, Facebook, had literally done an overnight switch from nothing to 90% of protocol on their application, went over to QUIC. Impressive. And if we start looking around, in a little bit more detail, taking snapshots around the world, this is from 2022 again, but later in the year, we see that, first of all, it's mostly used for video streaming, at least in those particular times. It's mostly large volume flows, the number of flows. That's in 2022, and the reason I'm making the point is because the image is shifting as we go along. Okay, and the big five have to a large extent started to shift to QUIC. The big five being YouTube, Facebook, Instagram. The only holdout is Netflix. And there's a good reason why Netflix is a holdout, by the way. It's because Netflix has a very, very optimized TCP stack. You've noticed how quickly Netflix starts compared to everything else from a streaming video perspective. There is a large part of that is the optimization they've done on the handshake of the protocol stack. So they're fairly loath to actually give this up very quickly. However, we do know, because all of them are using actually the same video code infrastructure, it's the standard ABR video player, it's only one compiler switch to actually switch from TCP to QUIC. And shift to 2024 and start measuring all around the world, we're seeing that it's becoming more and more a dominant protocol. The other thing that is very interesting, you see, for example, the numbers in Latin America are showing bigger than the numbers in Europe and North America. That's very much because if you look more deeply into the QUIC usage, you'll find that it's mostly mobile apps that actually use the protocol, because it's the app rather than the browser. Although most browsers do support it as well, it's the apps that default to the protocol. And LATAM being very much a mobile-first type of region, this happens. We took some measurements in Asia-Pacific a couple of weeks ago. I haven't got them here, but they show some very interesting numbers. It's over 50% in Asia-Pacific. One particular area was a holiday destination, well-known holiday destination, very beautiful and everything. It was over 70% QUIC, 40% of that was Meta, of the total traffic of the place. So this stuff is taking over the world, because consumer traffic is taking over the world. If you look at average measurements, we see that it's trending to 50%, and it's waiting for the next big blip. The next big blip is the new generation of video providers, the TikToks, et cetera, who just started dabbling, as we're going to see, into the QUIC protocol, when they're going to decide to switch, because everybody has a good reason to do so. This is Amsterdam, so I thought that I'd find out what's happening in the Netherlands. So I actually took a measurement yesterday from 4 o'clock in the morning for about 7 hours in the Dutch network that I had access to. We can see that it follows very, very clearly the global trend. Okay, the global trend of about 40-something%, but a small thing that it makes Holland different than the measurements we were taking 2 years ago in other places in Europe is that the number of flows, of QUIC flows, is bigger than the number of, the volume, which is kind of an inverse. We said QUIC is being used for video mostly, right? And video is few large flows, not lots of. What are these short flows? Well, it turns out that there is a shift also in business traffic. Microsoft, we're going to see it later, Apple Private Relay, and a number of other players that now generate a lot more short flows are moving into the QUIC space, and therefore we're starting to see a lot more of short flow traffic as well, rather than just large flow traffic. And this is more prevalent in highly developed markets that are also not so much, while they might be mobile, they're still using applications rather than just business applications on their mobile space, rather than just consumer applications, which is what's happening in most of the other markets. So that's the situation in, sorry, oh, how do I go back? Okay, and as we said earlier, the big five are already pretty much QUIC dominant with the exception of Netflix, and everybody else is dabbling in it more and more, so it will happen. And why it will happen is going to be part of the conversation in the next section of this presentation. So, okay, it's QUIC. I'm pretty sure most of you being networkers know what QUIC is, so I'm not going to go through a protocol analysis or anything like that. What I am going to do is, however, show and discuss a little bit of what it does to the network and what we're observing. And a lot of the work that I'm going to be showing now has been done by our friends at AMS-IX in Australia, primarily Jeff Houston and his team, who's done some really, really cool measurements about how the protocol behaves under congestion conditions in the network. So we say QUIC, but this is really shorthand for an evolution of the total protocol stack above the IP layer. Okay? We're going from a well-known, well-defined based system, which is on TCP, TCP, a transaction-oriented protocol, running usually HTTP over it, another transaction-oriented protocol. That's the first thing that actually most of the app providers realized, that I'm doing two transactional things on top of each other. Why am I doing that? For something that's necessarily actually an RPC, why don't I invent an RPC-oriented protocol? That's why, to a large extent, they invented this. The other reason what they wanted to disintermediate everybody else, but we'll come to it in a minute. And we're moving to a new stack that essentially replaces the transport layer with something that runs over UDP, fire and forget type of transport, but is natively encrypted at TLS 1.3, which means no man in the middle, perfect forward secrecy, etc., etc., etc. Using an HTTP 3 usually protocol, that's the default now in Azure, in Google Cloud, and most of those places. But then also tackling all the other visibility aspects of the protocol. DNS interception, gone. Most of the DNS traffic is already moving into DNS over HTTP. When you type an address on your browser or when your app sends a request, it doesn't go through 53 UDP or 53 TCP. It goes over an HTTP connection to its own preferred DNS provider. 50% of global DNS requests are being served by Google and Cloudflare. 80% are being served by by Google, Cloudflare, Apple, IBM, and a couple of other players directly over DOH. Firefox, as we're going to see, is defaulting DNS over HTTP directly as soon as you install it anywhere in North America. It's a going trend. So visibility of the destination and also the ability to load balance at the network level by actually sitting on the DNS hierarchy or spoof or whatever is disappearing very rapidly. But we still had some visibility capabilities into the traffic through things like server name indicator, SNI, or the client hello. All those are also being taken away through a series of RFCs that are encrypted SNI, and then on top of that, encrypted client hello. So at the end of the day, any capability we had to do any kind of packet inspection to understand what is happening on the network, and therefore make some decisions, traffic engineering decisions, policy decisions, or whatever, are being taken away from us. And they're being taken away from us because, very, very rightly from their point of view, the application providers are saying, I want to control absolutely the user experience of my user. The subtitle is, I don't care about anybody else, unfortunately, but it's an unfortunate but logical corollary. So what happens when this thing starts? Uber demonstrated it, I think, starting at the bottom here, in probably the best way possible. They went to India, which is a fairly difficult network to begin with, especially in the mobile space, and that's like 5 years ago. And they had two versions of their app going around, one of them written in TCP, the other one written in QUIC. They found that the worse the network, the better the improvement of the QUIC app. So the user experience of their user when they fell down into Edge or 2G, anybody remember GPRS? It was actually, the improvement was 100%, 150%. It was amazing. And this is what is driving the whole exercise, okay? Look at the behavior of QUIC flows when coexisting with our good old, the ones that we love, TCP flows in the network. You put them together, QUIC is more aggressive by default, very fast off the blocks, starts quickly, and then starts elbowing everybody out the way. So under exactly the same conditions, it'll take about twice as much bandwidth on the same link as a TCP flow. But the fun part is when you start adding flows. The TCP flows that we all know and love start behaving nicely. Hey, I need to be nice to the other guy. Somebody's dropping my packets, I'm going to back off, we're going to share, and then the QUIC flow is just pushing everybody out of the way and gaining and gaining and gaining. Why? Because flow control has actually moved from the network protocol to the application. They're still using BRR, or Reno, or Prague. Well, not so much Prague, to be honest, but mostly BRR and Reno. But they control the parameters at the application level, and they control the response when congestion is sensed. YouTube does a really cool thing. They actually monitor a flow to the user. When they see congestion in the form of drops and retransmits to a user, instead of backing off, as a normal TCP flow would do, they open 3 more or 5 more parallel connections, just dumping data down there. They don't care about a sequence of or anything because the application will actually resequence everything. But what they care about is, can I fill the buffer of my application as fast as possible so that my user is never going to experience a stutter? This is fundamentally why QUIC is being used in the video space so much, but not only because what we just described works also in the application space quite happily. And where it has a lot of impact is wherever we have shared bandwidth. And there's 2 big places of shared traffic bandwidth. One is obviously the wireless access, where all our phones are sitting. The other one is the peering points, where a lot of traffic is coming in, and it's going through a single pipe, and then it's being spread out into the network. So these are the places that we want to be careful. Now, that's about traffic behavior, but QUIC also is now acquiring a very interesting aspect in the security space, because there is something called MASK, which is a series of RFCs that essentially, if we boil it down to, transports any kind of traffic, including even IP, over HTTP3 over QUIC. It might sound like a horrible monster, right? Running IP over HTTP over QUIC over IP, right? But it is the ultimate exfiltration tool. Nobody will ever block HTTP3. Everything is TLS 1.3 encrypted. So this traffic will go through no matter what. More than that, it is going to be totally invisible in terms of source and destination. Any of you have used that might have used the Cloudflare 1.1.1 application on your phones or on your tablets or whatever, you can turn on the VPN feature, right? That VPN feature is a mask proxy that takes you directly to Cloudflare and runs all your network over a completely invisible encrypted connection through Cloudflare, hiding everything in the process. Mask is really cool because it can work in everywhere. It can work inside the app. I can run I can pull a mask proxy, put it in my app, and mask everything. It can work in the OS, multiple operating systems already support it. It can work as a client, but it can also work as an external proxy. So the deployment models of mask and how that essentially can break all kind of VPNs and security and whatever are a very interesting thing. Apple is one of the biggest users of it. Apple Private Relay is actually a split mask proxy model, which essentially uses a mask proxy from your phone or your Apple device when you use Private Relay to go to the Apple network, and then uses a mask exit proxy on the other side to reconfigure the traffic into IP to send it to its destination, hiding everything. Apple uses this as an identity service. That way, I will hide your identity, I will hide your data, I will give you privacy. Very, very worthwhile, but it has a lot of impact because actually now anything that we in the service provider space are doing that actually relies on geolocation, redirection, and whatever is being masked, excuse the pun, by Apple or the other mask type providers, and we're at the mercy of the IP addresses that they present to us to figure out what the best destination for a user is. So it becomes a very, very interesting conundrum and a battle between application providers, identity providers like Apple and Cloudflare and whatever, networkers that are trying to optimize their network, and everybody is actually looking for their own user to have the best user experience, right? This is really what it boils down to. Now, I talked about short flows earlier, right? They showed up really, really strongly in the Dutch measurements. One of the reasons is our friends at Microsoft, who have been wholesale transitioning Office 365 to QUIC over the last few years. In fact, there is even an MS-QUIC library that you can actually use to build your application, which is actually really well written, by the way. I've played with it a little bit. It's one of the better pieces of software that Microsoft has done in the networking space over the last few years. But now they've even done SMB file sharing over QUIC, which means that essentially you have full authentication, full encryption, super fast file sharing, because session establishment is like this when you're using QUIC, without a VPN. I'm not sure whether you guys have put it in production yet, but I know I've seen it's... no, it's not in production yet, right? But it will come, I'm pretty sure, because I've seen the work, and it's pretty impressive. The thing is, this is the transition of the QUIC protocol from a consumer space into the enterprise space, the high-value traffic space, from the low-value traffic to the high-value traffic space. And the only reason it's done is it is the user experience. Outlook Web Access runs better using H3 and QUIC than it does using H2 and TCP. End of story. So if it runs better, then people will use it. And that's why we can't block it. The standard reaction, especially in the enterprise space on QUIC, is, okay, so big deal. I'll block UDP 443. Yeah, did you listen to your users? They're going to find 100 ways to bypass you, so that you can they can actually get the better user experience. It's a fact of life. So this stuff is in business in a big way, okay, and it's being supported by all the major players in the market, and it's being used more and more, starting from the video space, but now moving into the application space, and whatever the user experience is important. It's also in the standards. None of this is proprietary. Everything has been ratified as an RFC all the way up to, it's a draft and including encrypted client hello and ESNI, as well as MASC, which is a whole raft of RFCs that are associated with it. So it's at scale, it exists, and it's taking over the world. So the question that we came back with is, okay, it's going to happen because, as I said, the users are observing the benefits. So the users always drive the result. You know, what's the golden rule in the world? Whoever has the gold makes the rules. The gold is the user that pays. Therefore, they're the ones that are going to make the rules. So if that's going to happen, the portfolio that we have in the ISP space when we're serving IP traffic is going to have to be rethought. What's correct and what's incorrect, what's the right products and whatever, is something that I'm going to leave to the commercial guys, or when I wear my commercial hat anyway. But it's going to have to be rethought. And it's going to have to be rethought because the information that's left might have some tooling, but it needs a different approach. So the questions that we got, and this is a real story, right? And it's about the second row, right? The CTO of Snapchat called one of the large mobile providers, no name said, and they said, I am going to instruct my users to actually go away from your network, all of my Snapchat user base, which is, you know, all the kids, right? I had to ask what Snapchat is. I have no clue. Honestly, I'm going to instruct all my users to get off your network because you are screwing up my filters. I had to ask again, what the hell is filters? Okay, so Snapchat, the way Snapchat works, you probably, younger generation know, they've got the streaming video flow, and then they've got the filters, the moustaches, the glasses, and whatever, but they have to be timed. Okay? Said service provider was actually doing a policy-based model, rate limiting the Snapchat traffic to a certain bandwidth. Good for them. They had the capability to actually detect what was video and what was not video by using deep packet inspection, so they would only rate limit the video, which manages the resolution. They wouldn't rate limit the downloads, except Snapchat switched to QUIC. And suddenly all that became invisible, and said service provider started rate limiting everything, and everything went out of sync. That was a huge problem for the consumer division. So they came and said, what do I do? How do I actually deal with this problem in its general version? Because some other people are actually benchmarking networks by seeing how fast a video downloads versus just streaming it, because a download is considered, a measurement so much, a good average measurement, so much volume, so much time. Okay, this is a fast network or a slower network or whatever. So they came up with this problem and say, okay, how do I generically identify and manage QUIC traffic and then mitigate its impact when it starts being unfriendly, as we saw. So there's some information that will never go away because it is still a routed network, and therefore you have to have a source destination address. So the famous 5-tuple will never go away. The packet size will never go away. The packet interval will never go away because it's just an interval, right? So this is the kind of information that we can always rely to be there so that we can do some things with it. And it turns out it's actually quite useful because traffic behaves predictably in the time domain. I mean, going back to the earlier problem statement, how do I distinguish between a Snapchat video stream and a Snapchat download, right? Well, it turns out that a video stream behaves differently in the time domain than a download. So if I have a mechanism of being able to do this in real time, I can actually start doing things like policy on a per flow basis based on the flow type rather than based on just where it's coming from or trying to look inside the packet that is no longer possible. So that's one piece of tooling, which is essentially a time domain flow recognition mechanism. It's not going to give you back 100% of the visibility of the traffic, but at least it'll give you back classification of what kinds of traffic you're running through your network, because Office 365 QUIC traffic is going to look a lot different than Microsoft, some form of video delivered on the Azure network, even though they're coming from the same set of IP addresses. And even if everything else is encrypted, you're going to know that, hey, that doesn't look like streaming video, that looks like something else. Maybe I should treat it differently than the streaming video stuff. So that's one piece of interesting information. The other thing that you can do, and I'm not going to use the dreaded word AI because it's just basic statistical anomaly detection, is find out if there is congestion. I know, sorry. AI is going to solve the problem of natural stupidity? Okay, well, let's not be too cynical because it's coming for all of us. Oh, thank you. That's a cool one. So the other thing that you can actually use is basic, essentially anomaly detection on the evolution of a flow in time to understand if there is congestion along the stream of that flow. Why is that important? That is important because we need to change a little bit the way that we think as networkers. In the networking world, I'm already like 2 minutes over, so I apologize if I overdo it. Oh, I have 2 minutes. Oh, good. Oh, I'm not going to get done in 2 minutes. But we as networkers have a certain state of mind, okay? One state of mind is that all I care about is moving packets. Okay? I take a packet, I look at it, I put it in the output queue, I send it down, it's not my problem anymore. That relies on a very implicit assumption that if something happens, and when I put it in the queue fills and I drop it, higher-level protocols are going to respond in a predictable way. Assumption number one that has been negated by QUIC. Assumption number two, which is kind of in the world of a networker, is we tend to think in state machines. And state machines means that I actually have full knowledge and full control of everything that is happening at every time. But that assumption is a very non-scalable assumption, because the state machine in today, it was great when the ARPANET was the size it was when I was working on it, way back when, okay, but at the size of the internet, the state machine is too big. So having the ability to sense when I need to actually take action, as opposed to watching everything, being able to say, and congestion is about the only time when I have to take action, is another interesting piece of tooling that people need to look at in order to actually use these things, because it will make these things scalable. Okay? And then the third piece, of course, is you need to create a programmable traffic management environment where actions can be taken based on the observations that you have, which we already have. So the reason I'm making this point is we are also, from an SLA management perspective, from an assurance perspective, we tend to rely a lot on probes, on things like TWAMP, or even extended ping and whatnot to understand what's going on. But the problem with any kind of probe-based synthetic traffic is it only gives you an image of what's happening on your network, not on the application, at that moment in time. Not 1 millisecond before, not 1 millisecond after. So for all this to work, you need to be able to characterize the real traffic in real time, which has always been a big thing for all of us networkers. IPFIX, NetFlow. The problem was that it was non-scalable. Whenever you turned that stuff on, it took the whole network down as soon as the traffic went really hard. So finding a mechanism to do all that in real time for every flow, which is possible, we're experimenting with this kind of stuff, and we're getting some results on it, is something really, really important. So this is a kind of toolkit that allows you to build multiple use cases for this environment. The first one and most useful being, can I have a look at what is going on? All this really lovely information that I was showing you from measurements around the world is actually done in real time, being pulled out of those networks by observation, by tiny, literally tiny observation objects that are sitting and listening. They don't interfere in any way with the network traffic. They don't actually sit on the data path. They don't add latency. You just span traffic to them, and they do the thing in real time. This is one of the interesting experimental pieces that we're coming, hopefully, to market with in the future, giving a sneak preview. And then, once you've got that, you can do things like dynamic policy, you can do things like protection of traffic, optimization, all sorts of. There's even corollaries that you can do, because you're measuring quality of experience, and you can actually understand everything that's happening in terms of quality of experience and where it's happening in the network. You can start doing things like turning on and off radios in the mobile network without impacting quality of experience. This is a whole huge presentation. I'm presenting some of the stuff next week at another conference in the 90-plus minute version, where we're going to go into deeper detail. But the number of corollaries out of this is immense. So, and it scales because you only act when there is a problem. The rest of the time, you just watch. But you only move and act when there's a problem, which is kind of the change in mind in the state machine that we need to put in our heads. So I almost did it on time, because the conclusion that we're drawing so far, and everything changes every 6 to 9 months, there's new stuff that comes in. The whole Microsoft stuff is something that we picked up in the last 9 months, even though it's been around for a couple of years in different ways, but it's getting to be in volume in the last few months. So I hope to be enriching this in many ways. But traffic is encrypted. Applications have taken control of the traffic behavior, and everything else is getting obfuscated, okay? The classical techniques that we've had, and especially in the telco space, DPI, rate limiting, and all that stuff, gone for at least 50% of the traffic, and it'll be gone for the rest of it sooner rather than later. And therefore, the consumer offerings and the management of peering points. I mean, I have a use case in Australia, actually, which is very interesting, managing peering points when you have rate limits in the peering points because everything over the rate costs a lot of money, as an example. And what we think is that a network-centric, IP-centric, getting as much information out of the IP flow approach is actually feasible and can generate both existing use cases but also new use cases, and making the IP network a very, very powerful actually tool in managing the whole network, not just the IP transport. I mean, kind of jokingly, 4G, 5G, PON, fixed wireless, it's still all IP to me. Thank you very much.
Herb, thank you very much. My brain hurts trying to keep up with.
You should see mine.
That was fantastic. Thank you very much, Andreas. Are there any questions in the audience? Yes, immediately. Another. And Stavros, yeah, of course.
Knock, knock.
Hold on. Can we turn this one on?
Who's there?
Okay, you're just going to have to shout. I'll repeat it. Is this one working? This one?
1, 2. Yes.
Perfect.
Hi, Andreas. Stavros from AMS-IX. Amazing presentation. Fascinating, very inspiring. Thank you very much. I really enjoyed it. But based on your experience and this story, and of course the summary that you said at the end, one question came to my mind. So with all your experience, how do you suggest networks navigate between the need for encryption in order to enhance the security and the need to visibility and monitoring the networks?
So this is where it's what we were saying towards the end of the presentation. Encryption is de facto. Whether we do it or somebody else does it, visibility into the traffic is or is going to be gone. So the point is exactly what you're asking. How do we use the information that we have and will always be there for us networkers, which is the IP layer, to actually manage traffic? And the first conclusion is we need to move to managing traffic as flows. Because there's another thing that I didn't say in the presentation because it becomes too much. Another thing that we're seeing in the global network at the moment is a stagnation of traffic growth. If you look at the numbers over the last year and a half to 2 years, growth, so step back for a moment, this industry was built and predicated on a version of Moore's law, which said that traffic will double every 18 months. And for the last 20 plus years, it's been happening. So everything has been about bandwidth, 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 bandwidth. Last couple of years, year and a half, we're seeing a big slowdown in the growth, and in some cases, particularly in Western Europe, and certainly in the EU, even a total flattening of the traffic. And there's a good reason why this is happening. If you think about it, the biggest individual flow that you can get today on the network is an 8K real-time video stream, and that's a 30 megabits stream, right? I can get that on the worst 4G network around on any phone. There is very little need for enormous bandwidth in the access. And given that we've saturated our users to a large extent in Western Europe, that means that this is flat. So there is a lot of bandwidth. Yet, the user experience is not perfect. The user experience is pretty bad in many different cases. So we need to figure out a way to use the bandwidth from a quality of experience perspective. So we need to shift from, oh, I'm moving my packets, and if it's congested, I'm going to drop them, and then I'm going to upgrade the link that actually got congested, to I'm monitoring the flows, and I'm trying to understand what's happening to the flow end-to-end in my network, and where can I do optimizations from a policy perspective and a traffic management perspective, as well as an infrastructure perspective. So essentially it's a rethink of how we design networks, systems. It impacts us as manufacturers. We need to think about how we design routers, because our current design model is predicated on exactly the same thing. All of the industry, not just us, right? If that makes sense.
Great, thank you. Yes, question at the back.
Yes, sir.
And over there.
Is it routers or routers?
Thank you for the presentation.
Not if you're in Australia.
Routers.
But it means something very different, apparently, in Australia, depending on the pronunciation. Sorry.
Thank you. I have a question. Do you think that the next step would be that the big content providers will start introducing methods to hinder statistical analysis?
Sorry, can you be louder? Look, the content providers will do what? I'm a bit deaf.
Introduce methods to hinder statistical analysis.
I doubt it. So another use case of doing this kind of analytics is security, right? And the whole idea around looking at the time signature of a fully encrypted flow to actually have an idea that it's some kind of attack and take some action. They have, the malicious actors, they have a lot of incentive to actually change the behavioral model. In the case of the content providers, both they don't have much of an incentive to do it, but because they're actually generating pretty large flows and they're relying from quality of experience perspective very much on the behavioral model of the video players, the ABR video players, how they buffer and whatnot, they're going to have a very hard time and low motivation, in all honesty, to actually change the temporal signature of their flows, which is what you're saying. Now, having said that, of course, if we start doing stupid things on our side, like starting hammering flows for no reason, I'm sure they're going to find a way to bypass us. But there are mechanisms. I mean, let me give you an example, right? Which is something that we've been doing for like 4 or 5 years already in mobile networks, so it's nothing particularly special, but it actually works really, really well. The reality is, if you look at how these applications work, right? YouTube is going to buffer 1, maybe 2 minutes of your incoming video in bursts, those bursts that I was showing over there, right? So why do they do that? They do it because when there is congestion, they don't want the user experience to actually change in every way. So what happens is, whenever they find bandwidth, the inverse, they actually blast buffer material so that they can feel safe. You as a service provider are sitting and seeing these things happening. So there's 2 things simultaneously. One thing is YouTube is blasting traffic, and you're sensing congestion in one of your links. It costs you nothing to actually take that YouTube flow and not police it. You don't drop packets. You just buffer it. You slow it down. You shape it for 200 milliseconds, 300 milliseconds. No more than that is needed, so that all the other traffic goes through, but its buffer on the other end has not emptied So that way you can, so there are cooperative ways, what I'm trying to say, to actually do this kind of traffic management. We've been doing it for quite some time in the market. Now, a lot of people say, why should I care? That's the problem of the application. I should care only about the packets. And yes, that's our traditional approach as networkers. But if we keep it that way, we're going to get more and more disintermediated from the quality of experience. And this is something that is what ultimately the user cares for, if that makes sense.
Great, okay. And we have one final question here. Yeah, okay. And this is the final question of More IP, everyone. So no pressure.
Wait. Anyone outside AMS-IX has a question?
Oh,
I'll take it.
now you get nervous. No, I was only teasing. No, go for it, go for it.
No, really, because all people from AMS-IX taking of the question is not now.
Does anyone else have a question?
Yeah, I'll take it up with Andreas privately.
Oh, okay. Yeah, you can ask it. Feel free to ask it. Did you have a question?
Yeah, I did have a question. Yeah, sure.
Okay, go for it then.
So you talked about, basically statefully tracking all of those flows that constantly head through, for instance, a service provider network. Do you think it's realistic to be able to track all of that information at such traffic volumes? For instance, looking at some implementations with TCAM, TCAM space is very, very valuable. Do you think, expanding those kinds of technologies?
You're not going to do it in TCAM space.
What, sorry?
You're not going to do it in TCAM space. No, absolutely. We've done it. We've done it in a number of different ways. It depends where you track it. One of the ways is semi-imaginary, shall we say, because obviously we're moving into slightly proprietary space here. But you can always, first of all, you don't need to look at the whole traffic. You only need to look at the headers, right? Because all the information is contained in the headers. So if you span the headers into a process that can process this stuff fast enough to do it without sitting on the actual traffic path, is one of the ways of doing it. Another way of doing it, which is very, very well known and common, is if you're sitting on the user plane of any kind of gateway, whether it's a mobile packet gateway or a BNG, assuming you have a clever gateway with a decent forwarding engine underneath, I would encourage all of you to go and look at the FT.io project in the Linux Foundation for something like this. You can plug a graph node on top of that forwarder and actually look at the traffic as it passes without actually interfering with the traffic. Just to give you an idea of sizes, with 1% CPU impact, I can actually characterize about 200 gigs of through traffic in this kind of model. So yes, there are ways of doing it, but it's not the classical ways that we were using with NetFlow, with IPFix and whatever, because indeed, those don't scale. You need smarter ways of doing it, absolutely. By the way, there's a reason I wear the Wile E. Coyote t-shirt, right? Okay, and the reason is we keep chasing the Roadrunner, and we just can't catch him, right? And the Roadrunner is all those clever things that are happening on our networks.
Brilliant. That's a lovely note to end on. Thank you very much, everyone. Andreas Enotiadis.